So we'll begin with a new topic. This topic is hidden Markov models. So the hidden Markov model, or HMM, consists of a number of states. And in this example, the number of states is 3. The states are A, B, and C. Now the states have initial probabilities, that is the probability of a sequence to start from that particular state. In this example, the 3 states A, B, C have starting probabilities of 0.1, 0.1, and 0.8. So we have a vector of initial probabilities, pi. And the total of all these entries of the vector pi should add up to 1. The HMM operates within a discrete time step framework, and in each discrete time step it transitions from one state to another, and these transitions are associated with probabilities. So what's shown here are the transition probabilities, and I have color-coded the transition probabilities, which are in arrows, based on the originating state. Therefore, the probability of transitioning from state A back to itself is 0.7, and from state A to state B in the next time step is 0.3. There is no arrow from A to C because the probability of transitioning from A to C is 0. So the probabilities can be arranged in a n by n matrix called the state transition probability matrix, where n is the number of states. So here P is a 3 by 3 matrix. And the sum of each row of P should add up to 1. 0.7 plus 0.3 is 1. That's because from any state A, you have to transition somewhere, so you need to have all the probabilities add up to 1. Likewise, from state B, again, the summation of probabilities is 1, and same with state C. Then we have a set of output symbols. In this example, the output symbols are X and Y, and the set of outputs is this set V. During each time step, the HMM is in a particular state, and it also emits an output symbol. And this output symbol emission is associated with probability 2. So for each state, there is an emission probability. In this example, from state A, the probabilities of emitting X and Y are 0.75 and 0.25. And likewise for states B and C. And all these probabilities can be arranged in a 3 by 2 matrix Q, which is the emission probability matrix. And as before, each row of Q should add up to 1. So these 5 entries, S, pi, P, V, and Q, completely define a HMM theta. The first 3 of them, S, pi, and P, are for any discrete Markov model, and the remaining 2, V and Q, are specific to the hidden Markov model. In the hidden Markov model, the state at which the HMM is in any time instance is hidden from view. It's unobservable or hidden. And what's visible or observed is the output. So from the output sequence, one has to infer various things about the HMM. So now we proceed to define formally what a hidden Markov model is. An HMM is a 5-tuple. Theta is, the HMM is given by S, V, P, Q, and pi, where S is the set of states which is hidden, and N is the cardinality of S, which is equal to the number of states, and each state will be denoted as S sub I. V is the set of output symbols which is observable, and M is the cardinality of V, which is the number of output symbols, and each output symbol shall be denoted as V sub k. P is the n by n state transition matrix, and each entry P sub ij is the probability of transition from state Si to the state Sj. And if t is any given time step, and if the state of the HMM at t is S sub I, then the probability Pij is the probability of it transitioning to state Sj in the next time step, St plus 1, or rather t plus 1. And each row of the matrix P should sum to 1, so summation j, Pij is 1. Qik is the n by m emission matrix, and each element Q sub ik is a emission probability if t is the current time step and the HMM is in state Si, then Qik is the probability that the output V of k shall be emitted. And summation Qik is equal to 1. And pi is the n by 1 initial state probability vector, and all elements of pi should add up to 1. So there are three basic problems associated with the HMMs. They are as follows. Given an output sequence, V1 up to Vt, where t is the total number of time steps, what is the probability of that sequence being generated by the HMM theta? And the algorithm to solve this is the forward algorithm or the backward algorithm. They are two algorithms closely related, and either of them can be applied to compute this probability. The next problem is as follows. Given an output sequence V1 up to Vt, find the most probable sequence of states that generated this output sequence. So there are various ways in which this output sequence could have been generated. The HMM could have passed through t number of states. There are so many different possible combinations of states that HMM could have gone through to generate the given output sequence. And the problem is to find which sequence of states S produced was most likely to have produced this output sequence V. And so the goal is to find argmax of all possible sequences of probability S given B comma theta. And the Viterbi algorithm is used to compute this argmax. The third problem is, given an output sequence V1 through Vt, what's the max likelihood estimate of the transition probabilities P and the emission probabilities Q that produce this output sequence. And when given multiple sequences like this, enough number of sequences, then also to find what's the initial probability vector pi. And so this is what needs to be computed. Theta ml equals argmax theta of P V given theta. The algorithm is the bound-Welch re-estimation, which is a form of expectation maximization, the EM algorithm. The end.